Section 2.5. Defining functions. Looking back to where the chapter begins, the snippet in Listing 2.2 contained a small function, add. Add takes two I32 values and returns their sum. The following listing repeats the function. For the moment, let's concentrate on the syntax of each of the elements in Listing 2.9. Figure 2.2 provides a visual picture of each of the pieces. Anyone who is programmed in a strongly typed programming language should be able to squint their way through the diagram. Rust's functions require that you specify your parameters' types and the function's return type. This is the foundational knowledge that we'll need for the majority of our work with Rust. Let's put it to use with our first non-trivial program. Section 2.6. Using references. If you have only used a dynamic programming language so far in your career, the syntax and semantics of references can be frustrating. It can be difficult to form a mental picture of what is happening. That makes it difficult to understand which symbols to put where. Thankfully, the Rust compiler is a good coach. A reference is a value that stands in place for another value. For example, imagine that variable A is a large array that is costly to duplicate. In some sense, a reference R is a cheap copy of A. But instead of creating a duplicate, the program stores A's address in memory. When data from A is required, R can be dereferenced to make A available. The following listing shows the code for this. References are created with the reference operator, or ampersand, and dereferencing occurs with the dereference operator, asterisk. These operators act as unitary operators, meaning that these only take one operand. One of the limitations of source code written in ASCII text is that multiplication and dereferencing use the same symbol. Let's see these in use as part of a larger example. Listing 2.11 searches for a number, the needle, defined on line 2, within an array of numbers, the haystack, defined on line 3. The code then prints 42 to the console when compiled. The code for this listing is at this location. For each iteration, changes the value of the item to refer to the next item within haystack. On the first iteration, asterisk item returns 1. And on the last, it returns 21,147. Section 2.7. Project. Rendering the Mandelbrot set. So far, we haven't learned much Rust, but we already have the tools to create some interesting pictures of fractals. So let's do that now with the listing 2.12. To begin, 1. In a terminal window, execute the following commands to create a project that can render the Mandelbrot set. A. CD $TMP or CD %TMP% on MS Windows to move to a directory that's not critical. B. Cargo new Mandelbrot --VCS none creates a new blank project. C. CD Mandelbrot moves into the new project root. D. Cargo add Noom to edit cargo.toml, adding the Noom crate as a dependency. See the sidebar entitled 2.2 in section 2.3.4 for instructions to enable this cargo feature. 2. Replace src/main.rs with the code in listing 2.12, which you'll also find in this file. 3. Execute cargo run. You should see the Mandelbrot set rendered in the terminal. So far in this section, we've put the basics of Rust into practice. Let's continue our exploration by learning how to define functions and types. Section 2.8. Advanced Function Definitions. Rust functions can get somewhat scarier than this example from listing 2.2. To assist those who are reading more Rust source code than writing it, the following sections provide some extra content. Section 2.8.1. explicit lifetime annotations. As a bit of forewarning, allow me to introduce some more complicated notation. As you read through Rust code, you might encounter definitions that are hard to decipher because they look like hieroglyphics from an ancient civilization. Listing 2.13 provides an extract from listing 2.14 that shows one such example. Like all unfamiliar syntax, it can be difficult to know what's happening at first. This improves with time. Let's start by explaining what is happening, and then go on to discuss why it is happening. The following bullet points break line 1 of the previous snippets into its parts. fn add_with_lifetimes goes to I32 should be familiar to you already. From this, we can infer that add_with_lifetimes is a function that returns an I32 value. Tick A, tick B, surrounded by angle brackets, declares two lifetime variables, tick A and tick B, within the scope of add_with_lifetimes. These are normally spoken as lifetime A and lifetime B. I:\tick A I32 binds lifetime variable tick A to the lifetime of I. The syntax reads as parameter I is a reference to an I32 with lifetime A. J:\tick B I32 binds to the lifetime variable tick B to the lifetime of J. The syntax reads as parameter J is a reference to an I32 with lifetime B. The significance of binding lifetime variable to a value probably isn't obvious. Underpinning Rust's safety checks is a lifetime system that verifies that all attempts to access data are valid. Lifetime annotations allow programmers to declare their intent. All values bound to a given lifetime must live as long as the last access to any value bound to that lifetime. The lifetime system usually works unaided, although every parameter has a lifetime. These checks are typically invisible as the compiler can infer most lifetimes by itself, but the compiler needs assistance in difficult cases. Functions that accept multiple references as arguments or return a reference are often when the compiler will request assistance via an error message. Footnote 6. Omitting lifetime annotations is formally referred to as lifetime elision. No lifetime annotations are required when calling a function. When used in a complete example as in the next listing, you can see the lifetime annotations at the function definition, line 1, but not when it's used, line 8. The source code for this listing is in this file. On line 2, *I plus *J adds together the referent values held by the I and J variables. It's common to see lifetime parameters when using references. While Rust can infer lifetimes in other cases, references require the programmer to specify the intent. Using two lifetime parameters, A and B, indicates that the lifetimes of I and J are decoupled. Note: lifetime parameters are a way of providing control to the programmer while maintaining high-level code. Section 2.8.2 Generic Functions. Another special case of function syntax appears when programmers write Rust functions to handle many possible input types. So far, we have seen functions that accept 32-bit integers, I32. The following listing shows a function signature that can be called by many input types as long as these are all the same. Capital letters in place of a type indicate a generic type. Conventionally, the variables t, u, and v are used as placeholder values, but this is arbitrary. E is often used to denote an error type. We'll look at error handling in detail in Chapter 3. Generics enable significant code reuse and can greatly increase the usability of a strongly typed language. Unfortunately, listing 2.15 doesn't compile as is. The Rust compiler complains that it cannot add two values of any type t together. The following shows the output produced when attempting to compile listing 2.15. This issue arises because T really means any type at all, even types where addition is not supported. Figure 2.3 provides a visual representation of the problem. Listing 2.15 attempts to refer to the outer ring, whereas addition is only supported by types within the inner ring. How do we specify that type T must implement addition? Answering this requires introducing some new terminology. All of Rust's operators, including addition, are defined within traits. To require that type T must support addition, we include a trait bound alongside the type variable in the function's definition. The following listing gives an example of this syntax. The fragment, shown here, says that T must implement std_ops add. Using a single type variable T with the trait bound ensures that arguments I and j, as well as the result type, are the same type and their type supports addition. What is a trait? A trait is a language feature that is analogous to an interface, protocol, or contract. If you have a background in object-oriented programming, consider a trait to be an abstract base class. If you have a background in functional programming, Rust's traits are close to Haskell's type classes. For now, it's enough to say that traits enable types to advertise that they are using common behavior. All of Rust's operations are defined with traits. For example, the addition operator, plus symbol, is defined as the std_ops add trait. Traits are properly introduced in Chapter 3 and are progressively explained in depth during the course of the book. To reiterate, all of Rust's operators are syntactic sugar for a trait's methods. Rust supports operator overloading this way. During the compilation process, A plus B is converted to A.add of B. Listing 2.17 is a full example that demonstrates that generic functions can be called by multiple types. The listing prints these 3 lines to the console. As you can see, function signatures can become somewhat convoluted. Interpreting these can take some patience. Hopefully, you now have the tools to break the pieces apart in case you get stuck down the track. Here are a few principles that should assist you when reading Rust code. Terms in lowercase, I and j, denote variables. Single uppercase letters, T, denote generic type variables. Terms beginning with uppercase, add, are either traits or concrete types, such as string or duration. Labels, single quote A, denote lifetime parameters. Section 2.9, Creating grep Lite. We've spent most of the chapter discussing numbers. It's time for another practical example. We'll use it to learn a little bit about how Rust handles text. Listing 2.18 is our first iteration of grep Lite. The code for this program is in this file. Its hard-coded parameters restrict flexibility somewhat, but these are useful illustrations of string literals. The code prints a line to the console. As you can see, Rust's strings can do quite a lot by themselves. Some features of listing 2.18 that are worth highlighting include the following. From here, we'll expand the functionality of our proto-application. Line 9, quote.lines, demonstrates iterating line by line in a platform-independent manner. Line 10, line.contains, demonstrates searching for text using the method syntax. Navigating Rust's rich collection of string types. Strings are complicated for newcomers to Rust. Implementation details tend to bubble up from below and make comprehension difficult. How computers represent text is complicated, and Rust chooses to expose some of that complexity. This enables programmers to have full control, but does place a burden on those learning the language. String and &str both represent text, yet are distinct types. Interacting with values from both types can be an annoying exercise at first, as different methods are required to perform similar actions. Prepare yourself for iterating type errors as your intuition develops. Until that intuition develops, however, you will usually have fewer issues if you convert your data to the string type. A string is probably closest to what you know as a string type from other languages. It supports familiar operations such as concatenation, joining two strings together, appending new text onto an existing string, and trimming whitespace. str is a high-performance, relatively feature-poor type. Once created, str values cannot expand or shrink. In this sense, these are similar to interacting with a raw memory array. Unlike a raw memory array, though, str values are guaranteed to be valid UTF-8 characters. str is usually seen in this form, &str. A &str, pronounced string slice, is a small type that contains a reference to str data and a length. Attempting to assign a variable to type str will fail. The Rust compiler wants to create fixed-size variables within a function stack frame. As str values can be of arbitrary length, these can only be stored as local variables by reference. For those readers that have prior experience with systems programming, string uses dynamic memory allocation to store the text that it represents. Creating &str values avoids a memory allocation. String is an owned type. Ownership has a particular meaning within Rust. An owner is able to make any changes to the data and is responsible for deleting values that it owns when it leaves scope. This is fully explained in Chapter 3. A &str is a borrowed type. In practical terms, this means that &str can be thought of as read-only data, whereas string is read-write. String literals, e.g., Rust in action surrounded in double quotes, have the type &str. The full type signature, including the lifetime parameter, is &tick static str. The tick static lifetime is somewhat special. It, too, owes its name to implementation details. Executable programs can contain a section of memory that is hard-coded with values. That section is known as static memory because it is read-only during execution. Some other types may be encountered in your travels. Here's a short list. Footnote A. Unfortunately, this is not an exhaustive list. Specific use cases sometimes require special handling. Char. A single character encoded as 4 bytes. The internal representation of char is equivalent to UCS4 or UTF-32. This differs from &str in string, which encodes single characters as UTF-8. Conversion does impose a penalty, but it means that char values are of fixed width and are, therefore, easier for the compiler to reason about. Characters encoded as UTF-8 can span 1 to 4 bytes. U8 within square brackets, a slice of raw bytes, usually found when dealing with streams of binary data. Vec of U8, a vector of raw bytes, usually created when consuming U8 within square brackets data. String is to vec of U8 as str is to U8 within square brackets. std FFI OS string, a platform-native string. Its behavior is close to string, but without a guarantee that it's encoded as UTF-8, and that it won't contain the 0 byte, or 0 times 00. std path, a string-like type that is dedicated to handling file system paths. Fully understanding the distinction between string and &str requires knowledge of arrays and vectors. Textual data is similar to these two types with added convenience methods applied over the top. Let's start adding functionality to greplite by printing the line number along with the match. This is equivalent to the -n option within the POSIX 1-2008 standard for the grep utility. See this link. Adding a few lines to our previous example, we now see the following line printed to the screen. Listing 2.19 shows the code that adds this functionality, which you'll find in this file. Listing 2.20 shows a more ergonomic approach to incrementing I. The output is the same, but here the code makes use of the enumerate method and method chaining. Enumerate takes an iterator, I, returning another, n and I, where n is a number that starts at 0 and increments by 1 each iteration. The source code for this listing can be found in this file. Another feature of grep is that it is extremely useful to print some context before and after the line that matches. In the new grep implementation, this is the $C num switch. To add support for that feature in grep Lite, we need to be able to create lists. Section 2.10. Making lists of things with arrays, slices, and vectors. Lists of things are incredibly common. The two types that you will work with most are often arrays and vectors. Arrays are fixed width and extremely lightweight. Vectors are growable, but incur a small runtime penalty because of the extra bookkeeping that these do. To understand the underlying mechanisms with text data in Rust, it helps to have a cursory understanding of what is happening. The goal of this section is to support printing out n lines of context that surround a match. To get there, we need to seg somewhat and explain more fully arrays, slices, and vectors. The most useful type for this exercise is the vector. To learn about vectors, though, we need to start by learning about its two simpler cousins, arrays and slices. Section 2.10.1. Arrays. An array, at least as far as Rust is concerned, is a tightly packed collection of the same thing. It's possible to replace items within an array, but its size cannot change. Because variable length types like string add a degree of complication, we'll revert back to discussing numbers for a little while. Creating arrays takes two forms. We can provide a comma-delimited list within square brackets, for example, this, or a repeat expression, where you finish two values delimited by a semicolon, for example, this. The value on the left, 0, is repeated by the number of times on the right, 100. Listing 2.21 shows each variation on lines 2 through 5. The source code for this listing is in the ch2-3arrays.rs file. It prints these 4 lines to the console. Arrays are a simple data structure from the machine's point of view. These are a contiguous block of memory with elements of a uniform type. The simplicity is still somewhat deceptive. Arrays can cause a few learning difficulties for newcomers. The notation can be confusing. Capital T semicolon n within square brackets describes an array's type, where T is the element's type and n is a non-negative integer. F32 semicolon 12 within square brackets denotes an array of 12 32-bit floating point numbers. It's easy to get confused with slices, T, which do not have a compile time length. U8 semicolon 3 within square brackets is a different type than U8 semicolon 4 within square brackets. The size of the array matters to the type system. In practice, most interaction with arrays occurs via another type called a slice, or capital T within square brackets. The slice itself is interacted with by reference, $T. And to add some linguistic confusion into the mix, both slices and references to slices are called slices. Rust maintains focus on safety. Array indexing is bounds checked. Requesting an item that's out of bounds crashes, panics in Rust terminology, the program rather than returning erroneous data. Section 2.10.2. Slices. Slices are dynamically sized array-like objects. The term dynamically sized means that their size is not known at compile time. Yet, like arrays, these don't expand or contract. The use of the word dynamic in dynamically sized is closer in meaning to dynamic typing rather than movement. The lack of compile time knowledge explains the distinction in the type signature between an array, capital T semicolon n within square brackets, and a slice, capital T within square brackets. Slices are important because it's easier to implement traits for slices than arrays. Traits are how Rust programmers add methods to objects. As this expression are all different types, implementing traits for arrays can become unwieldy. Creating a slice from an array is easy and cheap because it doesn't need to be tied to any specific size. Another important use for slices is their ability to act as a view on arrays and other slices. The term view here is taken from database technology and means that slices can gain fast, read-only access to data without needing to copy anything around. The problem with slices is that Rust wants to know the size of every object in your program, and slices are defined as not having a compile time size. References to the rescue. As mentioned in the discussion about the use of the term dynamically sized, slice size is fixed in memory. These are made up of two U-size components, a pointer and a length. That's why you typically see slices referred to in their referenced form. Ampersand, capital T within square brackets, like string slices that take the notation ampersand str. Note: don't worry too much about the distinction between arrays and slices yet. In practice, it's not material. Each term is an artifact of implementation details. Those implementation details are important when dealing with performance-critical code, but not when learning the basics of the language. Section 2.10.3 Vectors. Vectors, vec of t, are growable lists of t. Using vectors is extremely common in Rust code. These incur a small runtime penalty compared to arrays because of the extra bookkeeping that must be done to enable their size to change over time. But vectors almost always make up for this with their added flexibility.